Hi everyone, my name is Marco Fiore. I'm a research associate professor at India Networks. And today I will present to you our joint work with colleagues Cristina Marquez, Marco Gramaglia, Banchs, and Smoreda on identifying common periodicities in mobile service demands with spectral analysis. So let me start by providing some background. Our work concerns mobile services and the fact they generate today a huge amount of data traffic. That is estimated in 50 exabytes per month by Ericsson. This is the result of traffic generated by many different mobile services that have distinguishing time-varying demands. So the question that underpins our work is, how do the dynamics of demands for mobile services actually look like? And the answer to this question is very relevant since it has applications in technology and social sciences that span from dimensioning and managing mobile network infrastructure to, as an example, detecting land use. So previous works that tackled the same question can be classified into three large categories. The first one is that of services that study the aggregate demand generated by multiple services. The second category is that of works that focus on a single service and study it in isolation. The third category is that of comparative studies that confront different mobile service demands. And this can happen within the same class, like video streaming, or across classes. And in this last subcategory, we find works that analyzed and compared the demands generated by mobile services with respect to network key performance indicator, or from a forecasting perspective, or trying to understand and characterize the spatial temporal dynamics. And the last is actually our focus. So past works in that context tell us that mobile service demands generated by individual applications yield comparable geographic patterns, so have similarities in space, especially when we look at them at national and regional scales, while this doesn't hold over time, where they show basically very particular and unique behavior. So as an example, by running an activity peak algorithm on the time series generated by different services, we find out that they peak at different times of the day, and thus it's very hard to group them and identify similarities when looking at mobile services from a time perspective. And this is actually our goal. We want to understand better the temporal dynamics of mobile service demands. So to this end, we take a spectral analysis approach, which basically means that we shift the perspective from the time domain to the frequency domain, and study frequency components that describe the periodicity of mobile service demand consumption. So to this end, we start from service demands that are basically time series, in this case for Twitter. We pass them through a discrete Fourier transform and obtain the frequency component, so a description of the original signal in frequency. And we can plot, as an example, the power spectrum that tells us what's the relative power associated to each frequency component, is to say, to each periodicity in the original time series. Here you have a zoomed version that lets us appreciate how different components, so different frequencies, really have different importance for the original time series. And so we focus our analysis actually on a limited set of frequency components by keeping for each service only the frequency components that preserve 99% of the total power in the original signal, so in the original service demand. We apply this approach to measurement data collected in an operational network that covers the city of Paris. Data was collected for 3 consecutive months, and the demands are recorded actually for 37 individual services by using the packet inspection and fingerprinting. Those 37 services are in the top 50 in terms of the traffic demand they generate, and they cover an heterogeneous set of applications that span video streaming, gaming, social media, and so on and so forth. All the data collection and analysis was performed in full compliance with the GDPR and under the supervision of the DPO of the network operator, as well as CNIL, that is the National Privacy Agency in France. So, in order to explore a little bit the results we get from this spectral analysis, let's go back to the Twitter case I showed to you before. So we have again the power spectra, and we can observe in this power spectra two key behaviors. The first one is the fact that the power is accumulated at low frequency components. So it's only long periodicity that really matters to reconstruct the original time series, while high frequency components actually result in random noise. And by looking at the zoomed version of the spectrum, we can also appreciate that there exist very specific frequencies at which we have peaks in power. So only specific frequencies are especially important for reconstructing the signal. And the reason why I'm showing in detail this Twitter case is that this is the typical behavior we observe actually in all services. So by running this filtering of components I described before, we obtain, as you can see in the table on the right, that for basically all services, less than 10 components are sufficient to capture 99% of the original signal power, which is an interesting result because it tells us that actually there exist a very important periodicities that characterize each mobile service demand. Which brings us to the third part of the presentation that is concerned with clustering these frequency components. And the reason is that the spectra of the individual services actually have very similar high-level features, which is something you can see in the paper. This basically raises the question, can we find similarities in the few important components that characterize each service? And the way we answer this question is by performing a clustering of the components on the frequency and phase of each component. We don't use the amplitude here because we already used to filter the components, and also because we don't care about the magnitude of the periodicity, but really on its frequency and phase. So we devise an original two-step algorithm for clustering components based on frequency and phase. The first step is about clustering in frequency. So what we do is putting together, grouping components that have the same exact frequency. And this is pretty simple because frequencies are discrete here. So we just put together components that have the same frequency. And the reason why we don't put together components that have similar frequencies is that even a small difference in frequencies leads to a growing misalignment back into the time domain. So we really want to have the same frequency. And then in the second step, for each cluster of components with the same frequency, we perform a subsequent clustering on phase, so that we put together not only components that have the same frequency, but also have a similar phase. In this case, we don't need the phase to be exactly the same. A similar phase is okay. And to this end, we transform phase into unit Cartesian coordinates and run the classic dbScan algorithm on top of that. So by running this, what we obtain is that the over 300 original components, important components of our services, can be actually grouped in 16 clusters. And this is an interesting result because it means that there exist, in fact, a lot of similarities in the components that compose, that realize the demand of each service. So you have on the right an illustration of those 16 clusters, which don't have the same size. So some clusters are pretty small and only contain 3 components. Others are very large and contain 35 components out of a maximum of 37, because no single service can have 2 components in the same cluster, because it cannot have 2 components with the same frequency. Not all components are actually clustered, so end up in the 16 clusters. There are over 100 components that are unique So they are outlier, cannot be clustered because they correspond to unique time dynamics. So by analyzing these clusters, we draw a number of insights. Some of those are pretty expected. So we found out that almost all services have a dominant, very dominant component with a 24-hour periodicity, which maps to the circadian rhythm of human activity. So we have an alternance of low traffic overnight and high traffic over the day, which is again pretty expected. Another component or cluster that we actually were waiting for, were looking for to have, and that characterizes half of the services is that the one that maps to a weekly periodicity due to the alternance of working days and weekends with different behaviors. But we also identified some components, some clusters that we did not necessarily expect, such as a cluster that characterizes basically all services and that has identifies, let's say, a 12-hour periodicity, which means activity peaks occurring twice per day, or the fact that many services actually have regularities at a periodicity close to 5 hours. The reason underlying this periodicity is a matter of future research, but this is definitely something that is worth investigating. Also, several services defied classification, so their components didn't cluster, which means that those services have actually periodicities and phases that are unique and that make their time series not comparable with the time series of other services. And those were mainly mobile gaming, audio streaming, one very specific video streaming service like Netflix that is has unique characteristics, peer-to-peer services, and adult services. So to conclude, the takeaway message for this work is that by using spectral method, we can actually identify common periodic behaviors in the demands generated by different mobile services, which were not previously identified with analysis that only focused on the time dimension. And let me say that this work and all the results are at an early stage, so we are still working on this. And we have ongoing activities, especially focused on using wavelet transforms to analyze the demands, not only in the frequency domain, but at the same time in the time domain as well. So we draw power scalograms and identify ridges and perform clustering based on the ridges, and results are pretty promising to date. And then once we have this proper understanding and full understanding of the temporal characteristics of the mobile demands, then the next steps will be identifying the root causes for those dynamics, assessing the generality of the methods at different geographical scales, as well as the ultimate goal, which would be exploiting the results in terms of identify similarities and complementarities across mobile service demands for applications in network management and resource allocation. Let's conclude my talk. Thank you very much for listening, and I'll be happy to answer your questions during the online session. Goodbye.